Hello, everyone. It's time for more chemistry. This time, let's talk about oxidation and reduction reactions. Okay, the most important thing to know is that oxidation means the loss of electrons, and reduction is the opposite. Reduction means the gain of electrons. And so there's lots of different ways of remembering these two important facts. One is to remember the acronym or the memory aid oil rig, and that oil stands for oil is loss of electrons. Reduction is gain of electrons. You can also remember that Leo says grr, Leo the lion, loss of electrons is oxidation. And the gain of electrons is reduction. Oxidation reduction, that's a lot to say. So what some people do, a lot of people actually do, is they take the RED from reduction and they put it here and they grab the ox of oxidation and they make up a new word. And we just call these redox reactions. It's just the nickname for oxidation reduction reactions. However, at the core of these reactions is electron transfer. Somebody's losing electrons, but where are they going? To somebody else who's gaining them. So in a sense, electrons are just transferring from one substance to another. Cool. And knowing that really helps you understand these reactions and gets you through this part of chemistry. So either your oil rig or your Leo, remember one of those. And guess what? If they don't work for you, try these two. I'll do what I can. See whatever works. Okay, let's investigate a specific redox reaction, an oxidation reaction. Here's a cool one. I got nice pictures here. This is kind of ordinary. We're going to make table salt. But if you want to do it from the initial pure elements, this is how you do it. Go get some pure sodium, and that's kind of cool. You really don't get a chance to see sodium in its natural state. This liquid right here that you see in here, that's not water. Water reacts violently with sodium. That's oil, just mineral oil, pure oil, and oil and water don't mix. So is helping protect the sodium from water because there's moisture in the air, humidity. Yeah. So submerge this metallic sodium, pure sodium in its elemental state underneath this oil to keep it away from reacting with air. Oxygen from the air will react with it, as well as moisture in the air. Okay, so take a clump of this metal and then take some pure chlorine. So chlorine in its elemental state, its pure state, exists as a molecule. Two chlorine atoms bond together, covalent bonding, right? We have a pair of non-metals. Okay, that's natural pure chlorine exists as this green gas here. It's contained in the flask. And then take a little piece of this metal, throw it in here, and they'll actually ignite. I think you need a little something to get it started, some little catalyst or an initiator of sorts. But once the reaction gets going, the inside of this flask will just be covered with these white crystals that you can scrape out, and you know it as table salt, sodium chloride. Cool. Okay, so now how is this a redox reaction? Well, let's look a little more closely at what the molecules and the materials actually consist of. We're looking for electron transfer. We're looking for Leo, loss of electrons, or we're looking for grr, gain of electrons. And the best way to do that is to follow charges. So let's identify any charges on these substances as they react, and we'll look at the product too. So what do we got? We got metallic sodium. Well, that's straight off the periodic table, which I have over here. Yeah, so sodium is element number 11, which means that sodium atoms have 11 protons. And then in the natural state of sodium, it has an equal number of electrons. Wait, equal numbers of electrons, that means there's zero charge, right? Yeah, that's true. Also, if it had a charge, we would see something written right up here in the corner, right? And there's nothing there. There's nothing, meaning zero. Yeah, there's no charge on these sodium atoms. How about chlorine? Well, a minute ago we said that non-metals bonding to non-metals make a covalent bond. That's sharing of electrons. A covalent bond doesn't have anybody with charge. These chlorine atoms also have zero charge. They're sharing electrons. One didn't steal electrons from the other to make an ionic bond. But what's happening here in sodium chloride? In this substance, well, let's go back to the periodic table. Sodium chloride, well, here's sodium on the left side. Here's chlorine on the right side. But more importantly, in the upper right of the periodic table are the non-metals. Sodium is a metal, and when a metal bonds a non-metal, we expect ionic bonding. And if it's ionic, somebody's positive, somebody's negative. Okay, so that's something you should know. Ionic bonding, yeah, means there's a cation. Which one's that? Cat, meow, is positively charged. And metals tend to be cations. They like to lose electrons. Wait a second. Yes, metals tend to lose electrons to become cations. Chlorine is a non-metal, and the non-metals tend to gain electrons. That sounds like the GER part of Leo says GER, gain of electrons is reduction. Ooh, yes it is. Chlorine wants one more electron to be like argon. Remember, the noble gases are in the last column. They're called noble, majestic, royal, whatever. They're special because they tend to have these magic numbers of electrons, these special numbers of electrons that make for very stable atoms. And we understand that to mean that their shells, the electron shells, are full and complete. Their whole, it's very stable, not reactive. And chlorine wants to be like that. So chlorine's task in life, I guess, is it starts with 17 electrons, it would like 18. It needs one more. Sodium is in column 1A with one valence electron. It wants to kick that out. Kicking something negative out of your life makes you more positive. Nice life advice there. It works in the real world too. So sodium's trying to lose that one valence electron. So instead of having 11 electrons, it can have 10 like neon. Ooh, and pretend it's a noble gas and be all nice and stable. Okay, I was looking for charges and we found them. So in one molecule, if you will, one formula unit of NaCl, the Na is a cation with a +1 charge, and chlorine is an anion with a -1 charge. And so, yeah, we did have an electron transfer take place. We started with the sodium with no charge. And after the reaction, sodium had a charge. How did it have a charge? What kicked out an electron? So before, the sodium had 11 protons, 11 electrons. Afterwards, it only had 10 electrons because one left. Sodium lost an electron. Where'd it go? Whoops, can't spell, can't write. It went to chlorine, right? So NCl2, HCl has no charge because we have covalent bonding, right? We can draw a quick Lewis dot structure. 8 dots around each atom make for a stable Lewis dot structure. And now this chlorine says, well, if I look at that pair of electrons, I feel like I have 8 electrons instead of the 7 valence electrons I had before. And this chlorine says, yeah, let me count that bonding pair also. And then I feel like I too have 8. One line equals 2 dots, 8 electrons. So they feel like they're noble now. They have an octet, no charge. But afterwards, chlorine said, hey, I'll take that electron. So after the reaction, each chlorine now has a net negative charge. So they gained an electron. So the chlorine that was neutral, each one gains an electron, becomes Cl minus. I would write, instead of just writing Cl, I would write the whole molecule. The Cl2 molecule gained electrons. And wait, we're talking about oxidation reduction reactions, right? So whether it's Leo, DiCaprio, or the lion, loss of electrons is oxidation. Loss of electrons, oxidation. Gain electrons, reduction. So to be all sciencey about it, sure, you could say sodium lost an electron, but be very proper, you should say sodium was oxidized. Because oxidation is loss of electrons. Oil rig. Cl2 was oxidation, sorry. Hang on, let me correct my grammar. Sodium was oxidized. There we go. Cl2, however, each chlorine gained electrons, or you could just say the whole molecule Cl2 was reduced. Because reduction is gain. Yeah. Oil rig reduction is gain of electrons. Cool. Okay. That's how we understand making table salt to be an oxidation reduction reaction. You think that would be good enough, right? And then the scientists come along, kind of complicate things a little bit. What's going on here? Okay, so there's terms that you need to be able to use correctly. So the first term here is oxidizing agent. So if you have an oxidation reduction reaction, you can point at one molecule and say, hey, there's the oxidizing agent. And that's a substance that's taking electrons. And we can also go through and look at the reaction and say, hey, that molecule or substance, whatever it is, ionic compound, whatever, is a reducing agent because it's giving away electrons. It's helping someone else get reduced. The oxidizing agent is something that helps something else get oxidized. So let's now label these molecules, compounds, elements as either oxidizing agents or reducing agents. By the way, these terms are usually only applied to the compounds on the left side, the reactants. Okay, so sodium, what are you doing? Are you stealing electrons or are you gaining? Well, sodium went to Na+. And we said just a minute ago that, well, I won't use the chemical name, I'll just say the chemical symbol. Na lost electrons is oxidation, Leo, lost electrons, oxidation, LEO. Okay, so hey, sodium, you lost your electrons. Where'd they go? They went to chlorine. So sodium, you help chlorine get reduced. It's the reducing agent. I'll come back to that in a second. Let's move on to chlorine for a moment. Chlorine, what are you guys doing? We're turning into chlorine ions. How are you becoming negative? Because chlorine is gaining electrons. Gain electrons is reduction, GR. So chlorine was reduced. Hey, chlorine, where'd you get those electrons? Oh, we stole them from sodium. Yeah, what'd you do to sodium? Oh yeah, we oxidized sodium. We forced it to lose electrons. So chlorine, you're the oxidizing agent. And I know some of you are like, okay, I get it, fine. Everything's opposite. Others of you are saying, what? I got a 50-50 chance. It's either oxidizing agent or reducing agent. Remember your definitions though. Pick oil rig or pick Leo says GR or even the Elmo one. Electron loss means oxidation, Elmo. And start with that. So sodium or chlorine, who's being oxidized? Sodium is. Oxidation is loss of electrons. Okay, once you figure out who was oxidized, they're the reverse agent. They're the double agent. Sodium was oxidized, making it the reducing agent. And then you can use the definition to verify that. Sodium, are you helping someone else get reduced? So he says, yeah, I'm handing over my electrons like this guy, handing over his electrons, cash. Chlorine, what's going on with you? Okay, chlorine is being reduced. It's gaining electrons. What did you do to the other compound? Oh, I stole those electrons. I oxidized the other one, helped oxidize. I'm the oxidizing agent. So everything's backwards. Identify what they're doing to themselves or what's becoming of them. They're either being oxidized like sodium, reduced like chlorine, and then flip it to identify the agent. You think that'd be the worst of it? Okay, but I think we can get it down. Rewind it or take a break and try and get that to sink in before moving on to the next part. Here we go. This is an example of a redox reaction, an oxidation reduction reaction, an electron transfer reaction. Why? It's hard to tell. How's it hard to tell? Well, oxidation is loss of electrons, reduction is a gain of electrons. So I'm expecting charges to be changing. If we look at this chemical reaction, we got methane, CH4. What kind of bond exists between carbon and hydrogen? Ionic or covalent? Well, let's go check out the periodic table. I misplaced it. Where'd it go? Here it is. Carbon, what are you, a metal or non-metal? Well, it's on this right side of the staircase. It's a non-metal. Hydrogen, what are you? It's the exception on the periodic table. I like this periodic table because the H is physically detached from column 1. It's kind of floating off the table. And that helps me remember, yeah, hydrogen's naturally a gas, and gases aren't typically metals. Yeah, hydrogen's not a metal. It's stuck over here because it has one valence electrons, one valence electron like the alkali metals, but hydrogen's not a metal. It's a non-metal. And some older periodic tables actually put hydrogen right here because it should be with the other non-metals. Bottom line is C and H are both non-metals. And if you have two non-metals, what kind of bond do you get? Covalent or ionic? Yeah, two of the same, two non-metals is covalent bonding. So in this molecule, okay, let's get the Bunsen burner on the screen. The chemical reaction is actually taking place in the Bunsen burner. Forgot to point that out. So in this little hose on the bottom left is natural gas. Natural gas is actually a mixture of compounds, but a majority of them, of the molecules in natural gas, is methane, CH4. And that's all covalently bonded together, which means there's no charge on any of the atoms. How about oxygen? There's two oxygens, they're identical twins, two O's. One can't steal from the other. They're also non-metals. This is covalent bonding. If you allow me to abbreviate COV for covalent. Carbon, oxygen, those are two non-metals again. Two non-metals make a covalent bond. All these atoms are covalently bonded together. Hydrogen's a non-metal, oxygen is a non-metal. Dang it, everybody is covalently bound together. There are no charges. So is there no transfer electrons? Well, there kind of is. And it has to do with electronegativity. So you remember electronegativity? Fluorine's the bully on the periodic table, likes to attract the bonding electrons, not share them very fairly. Let's not go in that direction, but that's the rationale of how this actually is an oxidation reduction reaction. So combustion reactions, chemical burning, and it doesn't have to be just with methane. Your body metabolizes glucose, blood sugar, with oxygen, and also produces carbon dioxide and water. So you don't have a little furnace inside you, but your body is technically going through a combustion type of process through metabolism, and it's all a redox reaction. It's electron transfer, oxidation reduction. Okay, so how do we figure this out? Where are the charges? Well, someone very clever, I don't know who, more clever than I, said, hey, let's make up charges. And let's not call them make up charges. We're going to call them oxidation numbers. and it's totally fabricated. It's just a bookkeeping method of how we can keep track of the electrons that are getting transferred. So you do need to memorize this set of rules. It's not too bad. I like to think of it as a new game. So hey, what are the rules of the game we're going to play? Yeah, let's play the oxidation number game. Okay, here are the rules. If you have an element in its pure form, so we just had sodium metal in one of our reactions earlier. We also had oxygen gas. Well, these are materials straight off the periodic table. And they're in their natural state. Oxygen exists naturally as a pair O2. Okay, in that case, they don't have any charges. So let's assign the pretend charge, the oxidation number, equal to 0. Okay, so elements in a natural state, the oxidation number is 0. If you have a single atom ion, scientists, we love putting new words on every new idea. Single atom ions doesn't sound sciencey enough. So let's use the word monatomic. Yeah, it sounds much more clever. Mono, you'll remember, means one. Atom, building blocks of natures. Monatomic means one atom ion. For example, sodium is a single atom with a plus charge. Oxide is a single atom oxygen with a -2 charge. Yeah, these are single atom ions, monatomic ions. And what we're going to do is say, hey, the pretend charge, the oxidation number, is simply equal to the charge on that atom. That's rule number 2. Okay, rule number 3. We're going to have a lot of covalent bonding. If we didn't, we would just go and just see the charges like we did before. So this is going to be very common when we are assigning oxidation numbers. For atoms in covalent bonds, we're going to pretend they are covalent. It's true, they are covalent, but let's pretend they're ionic. And if they're ionic, here are the typical charges. Hydrogen, we're going to assign the oxidation of +1. Where's our periodic table again? It's over here on the left, below Leo. There it is. Hydrogen has 1 valence electron. It tends to lose it, become a cation. Remember acids? Yeah, acids are H plus donors, bases H plus acceptors. Hydrogen, if it goes ionic, tends to be a +1 cation. So let's just assign the oxidation number for hydrogen to be +1. Oxygen likes to gain 2 electrons. So let's assign the oxidation number to oxygen to be -2. It's not really a -2 ion, but if it was ionic, that's what its charge would like to be. There's one notable exception. And I'll try to avoid using it on my Chemistry 6 exams. I mean, the Chem 6 is the intro level, so we shouldn't have a whole bunch of exceptions. But you might see in the homework, or if you're taking a different class and you're reviewing oxidation numbers through this video, here's the exception. Hydrogen peroxide, oxygen, oxidation number, sorry, I can't spell. Remember for hashtag, this little tic-tac-toe symbol meant number? So the oxidation number is actually a -1 for oxygen in hydrogen peroxide. So that might be useful to you. I'll avoid that on my exam. So fluorine, it's one of the halides. Periodic table real quick. Fluorine, where are you? It's the bully of the periodic table, most electronegative atom. It has 9 electrons, but it would like to have 10. So it's all about trying to steal 1 more electron to be a -1 anion. Okay, so those are things to remember, and using the periodic table, which you always get on my exams, will help you remember. Oh, I put the periodic table on the right, so let me, I forgot. Okay, so remember assigning oxidation numbers. Hydrogen gets a +1, oxygen a -2, fluorine, and the other halides will get a -1 usually. If you see exceptions to it, it'll be pretty obvious because of the 4th rule with oxidation numbers. Okay, we've only talked about single atom ions and their elements. And then the atoms H, O, and F, when they're covalently bound together, there's a lot more elements that could be covalently bond. So what do you do with their oxidation numbers? You have to do a little math. What you want to do is calculate the oxidation numbers for other elements so that if you add up everybody's oxidation number, the sum of oxidation numbers for everybody has to equal the overall charge of the ion or compound. Okay, let's break that down, see what we're talking about. Okay, so here's hydrogen sulfide. Sulfur, periodic table now that I remembered, is on the, here's the periodic table up here on the right. Sulfur is over here on the right side. It's a nonmetal. Hydrogen's a nonmetal. Two nonmetals make a covalent bond. Yeah, so H2S, hydrogen sulfide, is a covalent compound. No charges here, but we want to see if it can do an oxidation reduction reaction. So let's assign oxidation numbers to the atoms in HS. Okay, so run through the rules. Do we have anybody in their natural state? No. There's two elements attached together. That's not natural. Not straight from the periodic table. We just need a single element out there. Is it a monatomic atom? Wait, no, we just said there's two atoms, not one. It's not a single atom ion. Okay, so we do have a covalent bond, and therefore there's two H's here. Each one gets assigned a +1. It's not really a cation, but it's an oxidation number of +1 for each hydrogen. And then now rule 4, fourth rule here, is going to help us figure out what to assign sulfur. What's its oxidation number? Well, you have to add up everybody's oxidation number so that it equals the overall charge, which should have been listed here, and it's not because it's 0. This is a neutral compound. So we need the +1s of all the H's and the charge, the oxidation number of sulfur to be something so that everything adds up to 0. Well, that means this has to be a -2, right? +2, -2, all the charges, all the oxidation numbers cancel out. So the oxidation number, if you allow me to abbreviate it, ox number of sulfur equals -2, and the oxidation number of hydrogen equals a +1. Hey, we played the game, we assigned oxidation numbers. Let's do another one. Carbon and oxygen within this molecule, which hopefully you recognize as one of the polyatomic ions. Hey, this is carbonate ion. Okay, carbon and oxygen covalently bond together because they're nonmetals. Also, because it's a polyatomic ion, your instructor should have told you that atoms in polyatomic ions are held together by covalent bonds. That explains why the C's don't separate from the O's when you dissolve this in water. Ionic bonds can break apart and dissolve as free ions, but if it's covalently bound together, they stay bound together in water, usually. Okay, so we don't have an element in natural state. It's not a single atom ion. It's a covalent bond, H, O, or F. Ooh, O. So if we have an oxygen in a covalent bond, we're going to assign it a -2 charge. So in carbonate, there's 1 C and 3 O's. Each oxygen is assigned an oxidation number of -2. That's what the rule says. What's carbon? Well, do the math. What's the net charge on carbonate? It's a -2. So all of these oxidation numbers have to add up so that you get -2. If you like algebra, you could say that the oxidation number for carbon is X, and then you have 3 oxygens, each with the oxidation number of -2, and that all of these oxidation numbers have to sum or add up to a net charge of -2. So you can do the algebra there. Or I like just this picture profile and just trial and error. It's like, hey, how do I get like this -2 to survive being not being canceled out? Well, let's just cancel out these -2s with a +4. +4 -6 equals -2. Yeah, that works. Let's see if the algebras are going to work. 3 times a -2 is a -6. Get rid of the 6 by adding it to both sides. Oh, yeah. 6 minus 2 is 4. X equals a +4. Good. The oxidation number, Ox number of C equals a +4. The Ox number of of oxygen is equal to -2. Yay, that's the oxidation number game. What do you do with it? Oh yeah, we're trying to figure out how to figure out that the combustion reaction is really an oxidation reduction reaction. Let's play the oxidation number game. Move this over here. Okay, so let's assign oxidation numbers to all the elements. So carbon, well, there's no guideline for you, but there is one for hydrogen. When hydrogen's in a covalent bond, each hydrogen is assigned an oxidation number of +1. Carbon, you got to get an oxidation number so that when you add up everybody, you get this net charge, which is nothing. S equals 0. So carbon, you get a -4 oxidation number. It's not a charge, kind of pretend charge, because C's and H's are covalent bound together. Non-metal with a non-metal covalent bond. But the oxidation number, carbon, get the pretend oxidation number of -4. Oxygen. Ooh, that's the elemental form of oxygen. So the Ox number of oxygen, each oxygen, I know there's 4 of them, but I don't care. I just want to know what's the number, oxidation number for one of them. It's the same for all of them. It's -2. Ooh, no, it's not. It's the elemental form. It's 0. Okay, what happened after the reaction? Well, now the carbon's sticking to oxygen. Oxygen sticking the carbon through a covalent bond, so we assign the oxygen a -2 charge. Sorry, an oxidation number of -2. Carbon then has to cancel that out because carbon dioxide has no charge on it. So it has to be a +4. Right? +4 -4 gives you 0, the net charge of carbon dioxide. Water. Well, there's 2 H's in one water molecule and an O. And actually, you can just use these assignments. Each hydrogen's a +1. The oxygen's a -2. And this better work. And it does. Right? If I add up all the oxidation numbers, 1 + 1 is 2. -2 is 0. Yeah, then that's the charge on water. Doesn't have a charge. It's neutral. Cool. So I found all oxidation numbers. Then oxidation numbers increase when oxidized. Or if you don't remember that, there's a whole bunch of ox things in here, oxidation numbers increase, then just say, hey, carbon, you started with a oxidation of -4, and afterwards, now you're +4. How did you get to be so positive? Well, in life, if you kick out something negative, that makes you more positive. So carbon, you act as though you lost all 4 of these extra electrons, and you lost 4 more. Okay, that really doesn't happen. Remember, the oxidation numbers are not charges. It's just a bookkeeping method that helps us understand that, hey, carbon lost electrons. It does. It used to be assigned an oxidation of -4, but now it's a +4 in the product. The oxidation number went from -4 all the way up to +4. It increased. So the CH4 molecule, the carbon in methane, was oxidized. Yay! Okay, so that's how you do it. How do you discover if this reaction is an oxidation reduction reaction? Takes a little work. First assign the oxidation numbers and then see if the oxidation numbers change. And if they change, if they increase, you found the compound being oxidized. Let's look at the other one. Well, oxidation reduction reactions happen hand in hand. If someone's oxidized, someone else will be reduced. And since there's only two molecules here, methane and oxygen, only two types of molecules. If methane's being oxidized, the oxygen molecule must be reduced. Let's verify it. Well, oxygen started out with an oxidation number of 0, but afterwards, all the O's are oxidation number -2. So, right, oxygen was ox number 0, then it went to ox number -2. Did it increase? No, it started at 0, went down to -2. It decreased. It was reduced in value. Yeah, it was also reduced chemically. O2 was reduced. Oxidation numbers, that helped us. Last thing we'll do here is assign agent status. Okay, who's the oxidizing agent? Opposite is opposite. So whoever is being reduced must be the opposite agent. Oxygen is the oxidizing agent, which means the other guy must be the reducing agent. Or you could start here. CH4 is being oxidized. It's losing electrons. They're being used to reduce the other compound. CH4 is the reducing agent. So I think that's everything here. This might be helpful, a little history lesson. I don't know, it's kind of interesting. Why do we have these terms, oxidation and reduction? Well, I think it comes from the old alchemists of the Middle Ages. You know, when they were trying to make swords and stuff, you know, someone would go out to the field, start digging up a bunch of rocks, trying to find rocks that contained iron ore. So they fill their cart with tons of rock containing iron ore, take it back to the village, grind it up, throw it in a furnace, and all this tons of rock is reduced to this metal. In the furnace, the iron would be melted down, and all the leftover pieces of rock is just, waste product. But you reduced it in size from all this rock to a small amount of metal. And maybe you make a sword out of it and you leave it out in the rain and it starts to rust. It starts, it got attacked by oxygen and it was oxidized by oxygen. And now your sword is falling apart, turning into rust. So oxygen from the air is damaging all this metal. It's being oxidized. And so that's where the terms came from, I believe, oxidation reduction. So I hope that's helpful to you. I'll see you in the next video.